Yes, so thank you very much for this opportunity to present the work that we've been doing. That completely fits in this I2B2 Transmart symposium, where we have been working on a project led by Zach, Sean, and Suzanne in the NIH Big Data to Knowledge network to work on creating a patient-centric information commons of standardized unification of research elements, the picture. And so what I'll be showing you is a small subset of this project, which is the Picture RESTful API that enable us to have a fully access to all the data. So as Zach mentioned you this morning, I2B2 and I2B2 Transmart are two elements that can be accessed through this API, but there's many other ones. And that's the whole point, is to be able to have the link between all those different layers of information. Looking at the precision medicine report, where they took the analogy of Google Map, where we all have today on our iPhone, Google Map, with all the different layers of information. And this works very well to have satellites, protocol, traffic jams in real time, the opening and closing hours in real time, everything centered by GPS coordinate. The idea of this report and what we managed to do in the context of this picture project is to create a patient-centric information commons for patient data. So not centered by GPS coordinate, but centered by patient identifiers across all those different layers of information. So the first thing we've done is to be able to integrate everything into central database common, and then how to access this data, how to make sure that we could have access to all these different layers, because in reality, we can't move all those different layers of data. Now, some of the data sets are too big to be able to move from one center to another one. So the idea is, how can we have a RESTful API to be able to access them across the network? And showing you the example of one use case of making the link between genotype data and phenotype data, where we can integrate any kind of patient-level data, for example, with the phenotypes, where they could be either registry or longitudinal EHR data, and then creating a baseline of the phenotype describing what the patient has on the one side. The same thing on the opposite with the genotype, to create from the different biosample a baseline genotype, and then to be able to, as needed for the research query, to go and and have access to those derived phenotypes directly from the API. The key point is to be able to first create those baseline genotypes, and then to have per research study to be able to define them, because the way you will define those derived genotype or phenotype will change per study, and depending on your research question. The whole purpose here is not to create yet another API or another database. The whole purpose is to have something that is useful and actionable today in order to do biomedical research. So that's why our driving force was really to be able to make sure that this could be useful straight away. So in order today in 2017, it has to respect with the FAIR principle to make sure that it's findable, accessible, interoperable, and reusable. So we use different stack of open source research infrastructure. Today, I'll present you what we've done in the context of the Picture RESTful API. And in 2 days, I have the opportunity of present you the whole picture, the whole framework with all those different components and how everything fits together to create one platform that helps to drive making the discoveries. So right now, I'll focus on the RESTful API. The first key point, because we have patient data, is to make sure that we respect the authentication and authorization. So what we use is a centralized federation authentication mechanism using Auth0 to make sure that we do not store any password. We use the enterprise identity providers across and using the professional emails, or when we have, because we also have projects with parents so that they can use public identity providers like Google, Facebook, to be able to log in within the platform and to make sure that they are who they are. And then, based on this, to be able to access all our platform, either the user interface of I2B2 Transmart or the RESTful API, and that's what I'll show you in demo, or the Jupyter Hub in order to do the reproducible science. So the first part, the authentication, and then the second part, the authorization, which has to respect with two standards, to make sure that someone who's first authenticated is authorized, to make sure that they are allowed to access this patient-level data, and all this to be works from the UI, but also, and the key point is from the API, so that any data point, you are authorized to access it. And the infrastructure I'll show you a live demo on will be on from using R in a Jupyter notebook to querying using the R API to be able to access 3 different databases that are located in 3 different servers on Amazon. So one using clinical longitudinal phenotypic data in I2B2, another one using full annotated exome in SciDB large-scale database, and the exact exome aggregation consortium database, which is not in the I2B2 format. It's a large 2x2 table, a giant 2x2 table, which is also accessible through the API, and how to make queries across all those different datasets. And so the key point is to see here the scalability, so that we could have, and that was the driving force of this project, that we could have any patient-level data. It doesn't have to be I2B2. I2B2 is great because it shows its success, but then we really need to, in order to be able to scale, into other database model, so that we don't force people to use the I2B2 model. That was one of the key points. So the clinical example I'll show you is using an autism clinical dataset, the Simon Simplex collection, where we have 2,800 families, where we have the proband, here the affected kid, with all the data on this kid, with more than 6,000 clinical variables, with all the also data from both parents and at least one unaffected sibling. So it's a quad family with a lot of clinical data and full annotated exomes on all the family members. So there's 8,600 full annotated exomes, annotated VCF, accessible through the API. And the clinical example I'll show you, something that is already known and discovered from this dataset, is that when you have, for a subset of this patient, a CHD8 gene mutation, you have a larger head circumference. So that's the only thing I'm asking you to remember. CHD8 gene mutated, you have a larger head circumference, and those are 6 of the 8 kids that are present today in the database, where we have the consent to show, of course, their photos. And you can see here the head circumference adjusted by Z-score. When you have a CHD8 mutation, there's a larger head circumference. So this is an example, looking at all those layers of information that we talk, the pancake, to go from the genotype, CHD8 with a mutation, and to look at the phenotype with a complex phenotypic data, which is an adjusted head circumference by Z-score. And now the demo of showing you this use case. Simon Simplex, HMS. So first I'll show you from the user interface of I2B2 Transmart how I can drive this query so that you can see the result, and then I'll do the exact same query using the API. And you'll see how we get, I hope, the same results. So from the user interface of I2B2 Transmart, I log in using Auth0, and in this case, I'll use my HMS credentials. And then to be able to access from the user interface all the clinical 6,000 clinical variable and the mutations. So for example, CHD8 with at least one de novo mutation, yes for 8 patients, drag and drop, no for 2,500 patients. So this is the interface of I2B2 Transmart, and then generate summary statistics. That's where I'm comparing 2 cohorts, one on the left with CHD8 gene mutated with at least one de novo mutation versus on the right in blue with no mutation. And then what you can see between both subsets is on the left. So you can see here comparison of age between the 2 subsets, sex, and race. Now I want to look at the variable head circumference. So I'm going in the most commonly used, and that's the power, as you all know, of the I2B2 framework, to be able to have hundreds and thousands of different clinical variables available, and looking at the head circumference variable, which is a continuous variable, 1, 2, 3, drag and drop on those 2 subsets, automatically it will do a t-test. And the p-value, so the t-test at 3, a p-value 0.018. So I'm asking you to remember this number, 0.018, where it compares the mean of 56 centimeter for the patient with at least one de novo mutation of CHD8 and 54 centimeters with no mutation. So comparing as, is this difference statistically significant? Yes. Am I allowed to do that? There's no adjustment here by the age. And so this is a rough, but that's how they did it in the paper. So this is a very, because there's a real signal here, I didn't need to do the stratification by age, and I still get some results. So on purpose, I'm showing you a simple example that was discovered using this dataset with a p-value at 0.018. This is to generate hypotheses. The user interface is not to be able to do a full-scale analysis. I'll show you how you can do the full-scale analysis using Jupyter Notebook with the API. But the first point is really to be able to touch the data with no line of coding. I use just the mouse to be able to have access to this dataset. And now what I'll be doing is to access the API. So I need to be authenticated to use it. And so on my user here, user profile, I have access to an API token, which is only valid 12 hours, BD2K picture API key. And this key, what I'll do now is to integrate it in, I'll first show you using Postman, which is a tool that enables to make API calls so that you can see, and if you can read it here, the API calls. So if, for example, I'm trying to use a wrong key, so for example here, SSS, then enable to start session, and I'm not authorized to access it. Then what I'll do is by accessing here, putting a success key, then accessing the resources. Here, what is connected, as I showed you, there's 3 different resources, 3 different databases, 3 different tools that are accessible right now through the SPI. The first one is SciDB. SciDB, where there's 8,600 full annotated exome right now, where we use, and the purpose of SciDB database that was created by Stoneberger, who created Postgres, is to have this column-based database that enables to do algebra directly in the database, so to have a full scalable variant store. And we can run all those different operators in the database to be able to access it. So the key point is, for example, the aggregate, count, approximation, average. So all this is exposing SciDB internal API, and the purpose is it's now fully interoperable with the picture API. So you have one place in order to make query across those different databases. So the first one being SciDB. The second one is Exact, where the different elements you can query are very different. For example, by gene, ensemble ID, transcript, string, region, where it's exposing all the variant data that Exact is providing through their database. And the third one is the I2B2 tree from I2B2, where you recognize all the API calls of I2B2. So we didn't create anything. We are just exposing through a common API. So you can recognize all the I2B2 language, parent, child, sibling, modifier, the dates, to be able to make the query per days, per string, all the greater or equal, like. So you have all those different resources available to make your query. So for example, now running a query where I have, what I'll be doing is accessing all the patients that have a CHD8 gene mutation, send. I have a result ID, result status of this query, because it's asynchronous. This one is a very short, quick one. So the data is available. In what format can I download the data? I can format this dataset in 4 formats: JSON, XML, Excel, and CSV. And then how I can download it, for example, in CSV, being authorized. And you can see everything was done through this URL only. So now I'm accessing this patient-level dataset right now in live with 1 line per patient in CSV, or if you prefer in JSON. That's it. So it's really to have something very easy to use, scalable, in order to have access to all those different data sets. And then now showing you the use case of how to look at the head circumference using now the Jupyter Hub that enable us to have multiple users, and I'll show you this in 2 days, where we have one Docker per user in order to create a fully scalable environment for research. And what we have right now is showing you, for example, the SciDB with R running on the backend to be able to run the query of being authorized CHD8 gene mutation, and then extracting the head circumference with only a few lines. On purpose, we didn't create a package where everything could be integrated in a package, but on purpose, we are exposing all the different lines. So in only 10 lines of code, you can have access to your data with the patient numbers, the head circumference, and the CHDA status, and then here to be able to run a t-test and get the results, and getting here the same t-test value and the same p-value at 0.018. The key point is what we make available for investigators is this example of templates of Jupyter notebooks showing how you can access it, and then you can change it, because running this t-test is, of course, you want to write a paper with this. It's only the beginning of your study, but then you know, and you can change it, so you can start building on a good foundation base to access whatever you want afterwards, and you can write it, and someone else will be able to run it. So that's the key point of this reproducible science, to be able to have the code with this example that is runnable across all those different platforms, and not just running on one postdoc computer. And now I'll show you my last 3 slides, 3 examples of collaboration using this API, with the first one with the BD2K Center for Causal Discovery, with Greg Cooper, Jeremy Espino, and Bennett Michael, to be able to have access between their API, where they have the Center for Causal Discovery with high throughput Bayesian network, and a causal graph. What we wanted to do is to expose our data using our API so that they can use their framework, and then we can visualize their results. And that's a fruitful collaboration in order to have a link between those 2 different APIs. The second collaboration is closer with the Dana-Farber Cancer Institute, with the DFC, the informatics team, with Adi, Melanie, Nancy, and John, who are present here today, of how to create, using this API, how to be able to very easily create a new 2017 user interface, or to access all this underlying data, which is much more user-friendly and much more scalable. So it's a great collaboration that enables us to be able to plug in multiple layers of component around this API and around all this underlying data underneath. And then the first example is where we ran, well, Zach ran, without telling us, a datathon of saying, hey, I'm giving away Amazon accounts for whoever is able to create a cool use case of using the API with another dataset, the enhanced publicly available dataset, where we have 10,000 clinical viable, 10,000 patients, and also the Simon simplex. How could you create a cool dataset using the API on Jupyter Notebooks? And those are the winners of the datathon, who first, they managed not to break the API into using this large scale, and so also to try to use and to help us in enhancing this. So that's what I wanted to show you. So this is a huge effort. It's only a very small subset of what is being done within Picture. So please have a look at the website. You can directly play with the API from using this URL. And this is a huge effort from my team, led by Jason and Wenjie, the 2 lead software developers. Jason on the API and software side, and Wenjie on the database side, in order to make all this available. So thank you very much.